Detecting health hazards in autonomous vehicles. We are Nicole, Mitchell, and Hannah, and our advisor was Dr. Bowie, and our client was Dr. Corey from the VME lab. So shared autonomous vehicles, or SAVs, are completely autonomous vehicles that don't need any interaction between the passenger and the car. They are currently in development, and they're expected to be introduced into the market within the next 5 years. They will have multiple impacts on the transportation industry, but some of them would be decreased pollution because they're expected to use mostly electric models for these cars. There will be increased accessibility for those who are visually impaired or for those who have other handicaps. And there will be improved road safety. SAVs are expected to save almost 30,000 lives per year in the US alone, and this is by decreasing the number of fatal car accidents. And most importantly for our project, there will be increased importance of passenger experience. Right now, cars are marketed and modeled around the driver experience during the operation of the vehicle, but obviously these cars won't have any drivers, so what will be most important to their acceptance would be passenger experience. And a large factor in passenger experience will be the safety and cleanliness of the interior of these vehicles. So a lack of driver supervision in SAVs can lead to substances and objects being left behind, such as sharp objects and weapons, biohazards from bodily fluids, drugs and alcohol, trash, spills of food or drink, and also personal items such as phones, wallets, and other bags. If any of these things are left in the car, they have the potential to impact the next passenger's experience. So the ride-sharing company or the owner of the vehicle should be aware if any of these things are left in the car, and they should have the opportunity to clean the car before it goes to pick up the next passenger. So this leads us to our needs statement of a way to address commuter health hazards in ride-sharing autonomous vehicles that identifies biological fluids, foreign objects, and potentially sick passengers using a combination of automated light sources, audio sensors, and image analyses to monitor potentially harmful changes to the interior of the car.
So as most of us know, 478 was a course designed to prepare us for the instrumentation and experimentation in 479. One of our tasks was to brainstorm desired functions of our device and objectives that we would like to accomplish. Entering the 2020 calendar year, our desired functions included identifying the presence of bodily fluids, spills, foreign objects, and passengers, and whether they may be sick. We also hope to see the entire interior and communicate with sources outside of the vehicle. A secondary desired function was to have a method of sterilizing the interior. Our objectives were that our detector suite would integrate well into a vehicle, minimizing the potential for damage to the device or harm to the passenger. It would be consistent, meaning that our device would have a low fail rate, and it would have a fast response. In other words, the automated detection of hazards would be quick. It would be inexpensive, and it could be practically implemented, meaning that it would be durable once in the vehicle. And of course, appearance is an important factor to the customer experience. So we will revisit these later and discuss what we did and did not achieve on these lists. This is the design that we built. So we have a Raspberry Pi that acts as our control device. It controls a camera and a black light and a white light and a thermal sensor. And so the thermal sensor identifies passenger presence. And to identify objects or spills or bodily fluids, we have black light and white light, which are turned on and off at different times before and after passengers in the car. And before the passengers in the car, we take an image using the wide field camera, both for black light and white light. And we do the same after a ride is over, and then we can compare those two images for later on. We considered adding a sound detector that would be machine learned and be able to identify coughs and sneezes, and maybe even identify different kinds of coughs that mean a different sickness. However, we cut this out due to time constraints.
So here is the final design in actual pictures. As you can see, our setup is in the first picture where you can see all of the components, our computer, our device, and our lights. And the second, third, and fourth are just close-ups. In the second picture, you can see the thermal sensor and the camera is poking through the egg crate for stability. The third picture shows our Raspberry Pi and our breadboard for electrical connections. And our fourth picture shows our LED, our relay, and our AC to DC converter. Unfortunately, due to an accident, our LED light and our relay were no longer able to be incorporated, so we used a lamp that you can see in the first picture instead.
So now let's go over the process flow of this device. So the first thing that happens is that our thermal sensor identifies the absence of passengers. Next, our white light is turned on and an image of the interior is taken. Then it is turned off and our black light is turned on and an image of the interior is taken. These images are saved and will be used later on. These are our pre-ride images. So the next step is the identification of a passenger via our temperature sensor, signaling that the ride has begun. Next, the temperature signals the absence of a passenger and confirms that the ride is over. So now that the ride is over, our post-ride images are taken using the white light and the black light, respectively. Next is our health hazard identification step. So this is where we subtract the pre-ride images from the post-ride images to identify changes. So if there are no changes, we will go on to the next ride and repeat steps 3 through 7. If there were in fact changes, then we can alert the ride-sharing company and send it in for inspection. So here is my best attempt at an artist's rendering of what this may look like in a vehicle. All components are to be housed on or in the roof. And this hopefully gives you a good grasp of what's going on here, that the lights are able to illuminate the interior of the car, and our wide field camera can also see the entire interior, and our thermal sensor would be aimed at our passenger.
For the actual data completion, our first test was image subtraction. We took the same device, a phone, and placed it in 3 different areas on our chair to see what the difference was between these 3 pictures. As you can see by these pictures and numbers, we had a very close difference between both the white light and the black light, which concludes that no matter where we put an object in these pictures, the white light and the black light difference will be able to pick it up every time. For the evaluation of the temperature sensor, we took 3 different tests on 3 humans and determined that the average temperature was, for a human, would be between 27 degrees C and 34 degrees C. Obviously, this is not body temperature, which is 37 degrees C, and probably had something to do with the air between the sensor and the human. Tests were also done on ice water and hot water, and to determine the extremes of the sensor. And it was determined that any temperature over 35 degrees C would be considered a serious hazard and an indication of fever. For white light versus black light, we also took fluorescent materials. So in the first column is an empty sandwich bag. In the second column, a sandwich bag is filled with invisible ink. And in the third column, a sandwich bag is filled with lubricating fluorescent jelly. As you can see by the numbers indicated, the white light difference did not find any difference between these 3 objects, but the black light did, which indicates that even if the white light misses bodily fluids, the black light will catch it. As a recap, the image subtraction returned consistent values for individual objects. The wide-angle camera was used to capture the entire interior of the car. As you could see in those pictures, not just the chair was focused on, but all of the surrounding area as well. The black light differences were consistently larger than the white light. This could be due to the reflection of light off the objects based on where the lights were placed due to this setup being non-ideal, or it also could be due to the fluorescence of the actual objects. The black light did enable the detection of fluorescent substances, so it will be efficient at detecting bodily fluids, and the temperature sensor is able to detect the presence of passengers and could be used as a potential to detect fever in those passengers. So the testing conditions did not allow for complete consistency. More rigorous testing is needed. We will need to test repeatedly so that we can get enough results to complete p-value tests, and determine the actual efficiencies of the sensors.
All right, so as we mentioned, we're planning on calculating a health hazard metric, which combines information from both the image analysis and the temperature sensor. And this will just be a number that will represent the cleanliness of the interior of the vehicle. So this table that you see here is how we propose to calculate the health hazard metric. As you can see on the left, there's point values ranging from 1 to 5, and these point values will be assigned to the different ranges that you see in the table. And how we are actually going to calculate the number is we will sum the point value over these 4 columns for a total out of 18. So as you can see in the table, the 4 things that we're considering while calculating the health hazard metric is the white light difference, black light difference, the temperature sensor, and the black light difference minus the white light difference. So for the temperature sensor, as Hannah mentioned, we're going to set a threshold of 35 degrees Celsius to indicate a potentially ill passenger. But since this is not a completely accurate way to determine whether or not someone has a fever and could be sick, we only assign this a point value of 3 instead of more so that it doesn't shift the health hazard metric higher. And then why we're considering the black light difference minus white light difference. As Hannah explained, the black light difference is typically larger than the white light difference, and this could be due to fluorescence, which could be because of the presence of a bodily fluid. And obviously, if there's a bodily fluid present, it presents a much greater risk to the next passenger. So to incorporate this risk into our score, we wanted to assign a point value for this specific difference. So as an example to calculate the health hazard metric, we looked at the example that Hannah showed of the plastic bag filled with invisible ink. In this case, the white light difference was around 15% and the black light was around 70. In doing this subtraction, you would get 54.69. So looking at the white light difference, it would be assigned a point value of 1 because it is less than 20%. The black light difference would be assigned a point value of 4 because it's in between 60 and 80%. And the temperature sensor would have a score of 0 because it was not considered in this test. And the black light difference minus the white light difference would give us a point score of 3. So adding these together, we would get a sum of 8 points for the health hazard metric.
Now we can review our desired functions and objectives to see what we've accomplished. So we are able to identify the presence of bodily fluids using the black light. And that is very important because there's a good chance that a stain would be a bodily fluid if the black light can pick it up, but the white light can't, which was covered on Hannah's slide. We can identify the presence of spills and foreign objects and passengers, all using the white light and black light, and the temperature sensor to identify passengers. We struggle with identifying potentially ill passengers. While we can identify their external body temperature, we did not take the time to do the sound detector, which would have made a much more robust illness detection. We can view the entire interior because we have a great wide field camera. We cannot effectively communicate to sources outside the car, although it would not be impossible. We would just need to rig our code to send an email and send the images or use Bluetooth somehow. A secondary function of ours was to sterilize the interior of the car. We did not get to that. We planned possibly using germicidal irradiation, using a very powerful UV light, but that adds a lot of danger to our device, even though it would not be turned on when a passenger is in it, in the car, but we decided not to use that. Integration for our objective, we're not sure because we didn't really get the chance to put it into an actual SAV or some sort of simulation of one. Consistency, this is a very important objective, and we can check the box on that because we had those images that we've shown that show similar results when we expect to have a similar degree of change. The only thing is that we did not have a big enough sample size to say that we have statistical significance of similarity across these results. Fast response, we definitely have fast response because after a passenger were to get out, this process would take less than a minute, which is great. It is inexpensive. We stayed under budget. Practical implementation. So it could be strong. We're not really sure. We didn't really focus on making it durable. We did a lot of jerry rigging to get everything to work, and performance was really our first priority. So it's certainly not waterproof either. And appearance, we struggle with appearance. However, that was because of the moving off campus, that we had to do a lot of quick fixes and stuff. If we had stayed on campus, we probably could have made a really nice looking device.
So for our conclusions, our system is very crucial to SAV safety and adoption because it will allow passengers to trust that the vehicle they're getting into won't expose them to anything dangerous. And the visual assessments using automated detection are the backbone of the cleanliness. And combining the image processing with other sensors is a very effective detector suite because it allows us to look at different components of the cleanliness of the interior of the vehicle. Our product has potential for very high demand, obviously with the situation that we're going through right now with the global pandemic. Public transportation poses a great risk to passengers. So having a cleanliness detection system similar to ours would be helpful for them to be able to identify these risks, and they'd be able to minimize them because they would know what they're dealing with. And also we would not have to, our system would not have to be completely automated. We could rely on employees from ride-sharing companies to visually assess the images that our system can take in real time. So this adds a human component to the decision of whether or not the car needs to be cleaned before it picks up the next passenger, as opposed to completely relying on a number such as the health hazard metric. So it helps avoid potential errors and missing certain things that we should detect.
So what would future work on this project be? We would want to survey potential consumers, see how they interact with the device, how they like it, if it's an inconvenience, if they feel privacy is an issue, and then address those concerns. We would also want to machine learn a sound detector to detect coughs and sneezes to indicate potential illnesses. This would be combined with our thermal detector so that we have a better indication of illness than just temperature. We would also create a database to save the images for later reference and proof of damage. This could be used by the car companies for insurance purposes. We would also create a permanent structure for consistent testing or implement it into an SAV. Obviously, from the pictures you saw, this is not the best setup, so we would want to do something to ensure that our tests are consistent and reliable every time and we're getting correct data. We would also incorporate the use of a thermal camera to identify passengers with fevers and also help identify those bodily fluids. This would be a good backup system, so if one thing fails, you have another thing that tells us when something is wrong.
So now for our acknowledgements, we'd like to thank Dr. Richard Corey from the VEMI lab, and also any of the students in the VEMI lab that helped us on this project. There were quite a few. He was our client, and his guidance was crucial to completing this project. Now for the biomedical people, Angel Hildreth works in the office in our department, and she was super helpful with budgeting and acquiring of materials, and we definitely couldn't have done it without her help. Dr. Bowie was our advisor. When we had some issues moving off campus, we had some mess ups in terms of electrical connections, and we needed his help to get a new monitor, and he was very helpful and got that to us. Dr. Caitlin Howell, she taught 479 with Doc Bowie and was great for the communication side of things and the writing side of things, and gave us so many ideas that we hadn't considered. And Dr. David Navant was our teacher for 478, and he did a lot to help us prepare for the instrumentation that was needed in 479. We'd also like to thank Marianne Schmidt-Hamlin, University of Maine class 1959. She supported this project financially, and we're very grateful for that. And thank you for listening. So we're looking forward to answering your questions. Thank you.